Hi everyone, thank you for coming. I'm happy to introduce Suraj. He's going to talk about dissecting the inline keyword in Kotlin. So please welcome him.
Thank you. Hi. Thank you. So I'm Suraj. I'm going to be talking about dissecting the inline keyword in Kotlin. Before I begin, a bit about myself. So I am an Android developer. I've contributed to Firefox, the Mongo Stitch SDK, and the Realm SDK on client as well. I was writing Java before, then I switched to Kotlin, and now I'm actually exploring Golang a bit. I did Android, and now I've moved to backend mostly. I am pretty active on Twitter, and you can email me questions about slides, etc., if you have. I work at a company called QTalk. It's mostly, it's a company about synchronous communication, making it fun. Like you can play games and browse the web together all over a call. It is 100% Kotlin client and backend code, and we are also the default dialer on Android. So it's pretty heavy engineering that goes onto, and all of it is in Kotlin. There are some links to it. Cool. So inline keyword. When we are actually writing a Lambda or something in Kotlin, the IDE mostly prompts us that try using an inline keyword for it. But why do we actually use it? Like, why do we need it? Why can't the compiler actually do it, like automatically for us? So basically, the meaning of inline actually goes for like placing things or arranging them in a line or doing things just like in a line. But if it's that simple, then why does Kotlin need a keyword for it? Like, why can't the compiler automatically do it for you? There are multiple aspects over here. If we can drill down mostly into the version of Java that actually plays underlining, then we can actually dig deeper into it. So Java version compatibility. Let's start with Lambdas. Lambdas, as we all know, higher order functions or anonymous functions. They were introduced in Java from Java 8. They are mostly implemented in Java using functional interfaces, and they leverage on a specific bytecode instruction that was introduced in Java 7 called as invoke dynamic. It's a pretty special bytecode instruction which does a lot of things around it. But since it was introduced in Java 7, and lambdas are pretty important in construct and programming. We lose a lot of stuff if we try targeting it to Java 8. So it's better, in order to have it working for Java version 6, etc., we need to have tools like retro lambda, etc. Now the question is, if we have tools like retro lambda and all of these components around it, why actually take up the effort? How does it even affect Kotlin? So the ideology around Kotlin is that it tries to do more things natively rather than using more number of libraries or tools around it. And why should we care, since it's Java 6 and we have Java 14 coming, and a lot of things have changed in Java world? Why even care about Java 6? The problem over here is that it's Android. So Android and Java 6 are Android is pretty much holding back the entire Java ecosystem altogether, because Java 8 and Android 7.1, which is Android 7 actually was the first version of Android which introduced Java 8. So yeah, we should care because of Java 6 and Android mostly. So that is the whole need of the inline keyword, is because you can't actually have it working below Java 7 and 8 actually. Yeah. So let's start with the why. How? So how does actually Kotlin achieve it? Since if we know that Kotlin compiles to Java bytecode, and if the bytecode instruction itself is not present, then how would Kotlin actually achieve it? So before we move there, let's once again dive into lambdas and closures and a few concepts around them. So Kotlin lambdas are actually different than the lambdas which you have in Java. Kotlin lambdas are mostly implemented using function types. So you actually have a class called functions.kt, which has which has interfaces from function 0 to function 32 based on the number of parameter arguments you have in a function, like function 0 having 0 arguments and function 32 having 32 arguments. There's actually an interesting keep for expanding it to function 255, which is the maximum number of arguments you can have in Java. And the reason why Kotlin does it this way is because in Kotlin, functions are first-class citizens. like null pointer exception is a first class, or nullability is a first class citizen in Kotlin. Similarly, functions are also a first class citizen in Kotlin, meaning that you can actually assign a function to a variable, invoke a function's object later on, pass a function to a function, etc., etc. And that's the reason why you do it this way. Closures, on the other hand, it's more of a programming concept. It's more related to a lambda. Anything which is outside the scope of a lambda, and if it's consumed inside, captured inside a lambda, then you call it a closure. That's just basic concepts which you're going to use further down the slide, so it's just good to have it clear. All of this, if you just see it programmatically once, I hope the code is legible. So if you consider this example, we're going to use this example throughout. So we have a function called as test lambdas, which has a lambda, my lambda, and we have this and we have this my big loop, which is actually the implementation of that lambda, which consumes a lambda, and you have this value enclosure, which actually does nothing but just prints the value inside the lambda, which is test lambda and the lambda value. So this is lambdas and closures. We'll move on to the next concept, which is call sites. So call sites, again, are mostly a concept which is related to lambdas, and it's basically where you actually call a call site. So mostly when we're actually debugging onto Kotlin applications using IDE like Android Studio or IntelliJ, we actually find an option for lambda function, which is if you press jump to source, you actually find two options, which is check the source or check the call site. So call site is basically where you actually call the function. There's a bug in this. There's a mistake in this code, is that there's no lambda actually, but still, yeah. So if print me was a lambda and it was being consumed, then IamGroot would be the calling site for that lambda. Non-inline lambdas. Before we actually see how lambdas are and what do they do, it would be a good point of reference to actually know how non-inline lambdas would look like, because there is a lot of unoptimization. Like, we'll actually get to see the difference between non-inline lambdas and inline lambdas. So we'll consider the same example as before. We have a test lambda, which is our lambda function. We have our my big loop, which is consuming the lambda, and it's going to iterate. Like, we have an int range, which is 0 to 50, both inclusive, and it's going to run a loop, and it's going to call the lambda for the number of times the loop is going to run. So this is the logic part of it, which is the test lambdas function, which is a lambda being called and printing a particular variable. This is essentially the logical part of it. Now let's take a step ahead and try decompiling this source code and assembling it into Java again. So if we do that, we see something like this huge block of code, which is a lot of compiler injected code, which we actually don't care about. But the interesting concept over here is that the test lambdas, our function, was actually compiled into a class which actually implements a function1 type interface. And we know function1 because it has one argument, so hence it's function1. If it had 0 arguments, it would be function0, and it extends a lambda. So your method having a lambda actually is compiled into a class now. Class extending lambda and implementing the function1 interface. And the logic for that particular lambda inside the invoke, which is just printing a particular variable. And if you see the call site, this is where the actual problem begins. The call site looks something like this. Again, it's a lot of compiler injected code, which we do not care for much. If you look at the lambda, like the lambda method being invoked specifically, you see the test lambda function called along with the lambda, which is actually a new instance of the particular class we just saw. The problem is here with the new instance is that it will create a new instance for every time the iteration, the iteration will run. And it has been converted into an iterable because of int range. Int range compiles to an iterable in Java. So that is a problem. So you'll actually have 50 instances or 51 instances technically of the inline function that is going to happen. It's pretty bad. And so this is the worst case scenario. But Kotlin compiler is a bit smart. It also has a semi-optimized scenario wherein if you don't have a closure, It optimizes some things because if you don't have a closure, it does not have to create a stack for you for every method in order to capture the variable that you have for that. So for non-inline lambdas without closure, you don't actually have to care about much because there will just be a singleton instance of that particular lambda. If we take the similar example as we've seen before, except for the closure, you can see that there's no closure. There's just println. You're just consuming the value of the lambda within the lambda. And if you try decompiling the source code, you see that, and you just print the call side because the lambda won't actually change. It's only the call side that actually changes. And you can see you don't have a new instance of it running every time. You just have a singleton instance being created. It's still a bad thing because functions are technically native or technically more of like a very strong construct inside Java. So like it would not be good if we have an instance of it every time, even though it's a singleton instance, because if you have n number of lambdas, you'll actually have n number of instances which you wouldn't have otherwise. Also, it's not the way how Java does. Java uses the invoke dynamic keyword, bytecode, which Kotlin does not, to maintain compatibility. So this is a worst case. This is a semi-optimized scenario where you don't have the new instance created every time. Now, how about inline lambdas? How do they look when you decompile them? Let's take a similar example from before where you have a test lambda and you lambda and the loop which is consuming it, the same number of iterations. All we do now is just modify it by adding one particular keyword, which is inline. And just put it inside the decompiler and just throw out, let's try printing the Java code out of it. And if we see, the code this time is different. You don't have, this is all that you get from it. You have no classes, you have no instances, you have no implementation of functional interfaces, no class which extends a lambda, nothing. This is the only thing which you get. You have two static functions, the test lambda and the myBig loop, which you actually had in Java as well. Now, here is the fun part which begins, is that if you see inside the myBig loop function, you see the value in closure. It's actually accepting the, so this was the worst case scenario. It's actually having the closure as well inside the lambda. It has the loop as well, but it has no instances, nothing. It's just like compiler copy paste. It's just, everything is inlined. It has taken the logical block from your lambda, taken it out, and printed it into your call site. This is the actual power of inline, and it's magical in many ways because this infrastructure forms the basis of many things in Kotlin. It forms the basis for sequences, which are equivalent to streams in Java. It forms the basis for, you have for each and all of these functions, and you have, in fact, anything which leverages on the Lambda architecture actually uses inline internally. You have coroutines also because of their entire syntax. You have keywords like apply, etc., etc. So it just doesn't stop there. You have other aspects as well. For example, one of the real power over here is type reification. So if we were to define how the reified keyword or the entire reification mechanism, it means making something concrete or having something survive through a lot of stages. So, and the context for it definitely is generics. So if you take Java, for example, how many of you over here know Java type erasure concepts in Java? Okay, so theoretically what happens is that anything inside angle bracket, once it's passed into the compiler, you don't have the instance of it at runtime. It's just Java, like the runtime does not know what type of instance it is. So consider this example over here. You have a list of string which is actually an array list, which is an instance of an array list. And if you try printing the instance of that array list, and if you try running this code, you actually get an error saying it's an illegal generic type for instance of. Because the runtime does not actually know, and the compiler throws you a warning for that, because the runtime does not know what type of instance it is. Because even though string is an instance of object, list of string is not an instance of list of object. But if we try changing list of object to list of string, or to just list, it works. Because it's still a list. You don't know what list it is, but it's still a list. So this is essentially the type erasure concept in Java. Now, how does it apply for Kotlin? And can inline help over here? So let's take a more Kotlin example over here. and see how things work. So consider this example. You have a generic function with called Reified test, and you are printing the type of the class, and you're matching if it's a string or not in very crude way. How many of you think this code would work actually? Like, any ideas? Like this code would work? It doesn't, because it again throws this same error, because Java and Kotlin both have the same problem. It says that you can't actually, it's not a concrete type, it's not a Reified type. Use a class instance. So we've seen many APIs and we've seen many libraries use class with a capital C, just so that they can actually do these type of operations on them. Now, what if we do something like this? We add 2 parameters to it, which is inline and Reified, and that's it. It just works. And if you see the internals for them, how do they work? Like, this is our actual function, inline, Reified, along with all the parameters in them. And if we decompile them, we decompile that particular source code, and we see this particular function, the test function, where the Reified test function is actually called. Sorry. You see that it's actually comparing string and string. It's not doing anything. It has actually taken everything from the logical piece of code, and it's just checking string, actually string to string. So it's going to return true for you over there, which is your actual desired result. And you still have the Lambda function available, which just checks for an object and a string, and it's going to return you false, because it's just there to maintain compatibility and to maintain the presence of the function so you don't get method not found exceptions. So this is how Reified works. And the original logic block always remains the same, which is what you are checking over here. It just doesn't stop there. The concept of inline over here, which is applied to functions, actually is extended to classes as well, which again essentially means that you can inline, like you can make things work during the compile time, make the compiler do some heavy lifting for you. So let's consider like the indef annotation. Any Android developers around? So have you, like, Android developers might have seen the indef annotation in the Android source code. So actually what it does is that it's a type of it's a way to restrict your type, which is only present in the compile stage, because there's an annotation processor which just removes it post compile, and you just have it during the working stage just to restrict your types. So the idea over here is is an amazing idea, because you just want something at the compile stage to restrict types. And they're essentially primitives. Half of the things that we do around these things are primitives. So that's how inline classes were born, actually. So you have compile time restrictions on objects. For example, this is a very bad example, but yeah. So you can actually take this as an example, and we can have, let's say, an inline class, which is actually a Boolean parameter which says that can a candidate have a seat or not. And that's it. It's essentially used to restrict types. It has a couple of advantages and disadvantages. Let's discuss both of them as we go. So the advantage is that it opens up an array of possibilities, again, to have things which Java could never have. Like, for example, you have unsigned integers, unsigned long, unsigned byte, unsigned, all the numerical parameters over here in Kotlin, which Java could never have. What it does over here is that it essentially just takes it, does some compiler tricks over you on it, and essentially just prints out an integer variable itself, because it's still an int, or it's still a long for an unsigned log. It opens up a possibility, and also it's true that inline classes make great database IDs, because you have, let's say, cat, and you have a database of zoos or animals or something like that. Every database ID itself is a long, but you have different IDs for different things. So in order to, since they are long itself, but you want to restrict the type of long, you can actually use inline classes to restrict the type of long. There's actually a very good blog post on this saying that inline classes make great database IDs. It reduces the need to create wrappers around primitives. You can always create custom objects, like I can create a custom, instead of using the indef annotation, I can actually create a custom object itself and have an integer inside it. But having wrapper classes around primitives are not the best way, because you are actually creating more instances. It's not a good memory practice to do the same thing. So it reduces the need to have wrappers around primitives. These are some of the great advantages of inline classes, but there are some disadvantages as well. The biggest disadvantage is that it has mangling. Why does it have mangling? Is because consider this inline class, which is the unsigned integer class. It's actually taken from the Kotlin documentation online. You take this function, which is a compute function which takes an integer, and you take this function, which is a compute function which takes an unsigned integer. Both of them, when they'll be compiled, they'll be the same function, which is void compute and integer. So now, since you have conflict over here for the naming, the compiler appends kind of a hash code behind the functions which use inline classes. You can actually see them once you see the compile code for them. I actually forgot to print it over here. This is my mistake. The second disadvantage with inline classes is that it still has an experimental status. It is not mature yet, for no reason why. And it sounds very similar to type alias. It's not actually type alias because type alias does not introduce a new type. They both are used for type restrictions, but type alias does not introduce a new type, whereas inline classes introduce a new type. So suppose you create new inline class for something, let's say a database ID for cats, then that would actually be a type during compile stage. Post compile it won't, but during compile stage it is. So the actual advantage of inline classes kick in when you actually use primitives. Otherwise it's just the same. You have the same. There are certain advanced concepts in inline as well. One would be cross-inline. They just control the degree of inline, like the inlining of the lambda that you want the compiler to do. Cross-inline is actually pretty interesting because it restricts non-local returns. By non-local returns, we mean you actually block lambda from returning the parent function. And the one which is not cross-inline does not block the same. Let's look at this example. So over here, the cross-inline keyword is present on the non-local return lambda, which is actually lambda function, and you have a normal lambda as well. And this is how the call site might look like. So if you look at it carefully, the non-local lambda return has two returns. One is that it returns the lambda itself. This operation is permitted because you're still returning locally, which is you're still returning inside the scope of the lambda. You're not actually trying to return outside the scope of the lambda, which is the function which is calling that particular lambda. But this would be illegal. This is what cross-inline actually restricts. It restricts non-local returns. That is, it restricts returns from the same returns from the lambda which returns to the lambda which are its calling function in a way. And theoretically, both of them would be possible inside the normal lambda function. There's another point to it, which is no-inline. No-inline, as the name suggests, does not inline the code base does not inline the lambda for you. If you ask what might be the reason to do this, the reason is simple. Since in Kotlin functions are first-class citizens, you might actually pass a lambda to a function, to a system API, or to some function which is not under your control. And if that function might not have been inlined, then there is no way for the compiler to actually inline it. In simple words, like if you are passing a lambda to a function which is not inlined, then there is no way for the compiler to actually inline it. So that's when you specify no inline. That's when the compiler will not do the optimizations for you in terms of memory and CPU. It will create more number of instances if you have a closure, or it will create a static instance if you do not have a closure. And if we consider an example over here, this is our no-inline lambda 2. This is a function which is not inlined, which actually takes a parameter as a lambda. This would be illegal. This function would be illegal if lambda 2 was not no-inline. Because again, as we discussed, the compiler has no way for you to actually inline it. That's it. There are a couple of links that are useful to this particular talk. There's a blog written on this. It's incomplete, so there's a link to it. There's a good read on inline functions in general. Invoke dynamic, it's a beautiful keyword that was introduced in Java 7. It does a lot of heavy lifting for Java as an ecosystem from Java 8. And inline classes, which make great database IDs, it's a blog post by Jake Wharton, who is, non-Android people might not be knowing Jake Wharton. And the app to my, the link to the QTalk app, the place where I work. I have a couple of stickers as well, in case you guys want to collect. And the link to this presentation. This presentation was actually called Power of Inline, and the title just changed overnight. I might be a bit fast, I'm sorry for this, but yeah. Are there any questions about Lambdas, Java, inlining that I have 10 minutes. Any questions? Anything? Yeah. Okay. Any questions, guys? No, I'm done.
Thank you.